In this question, I want to talk about class definition and the process that occurs when classes are defined. For those of you who have experience with programming languages like JavaScript or Java or C or C++, you might have the belief that there's a separation between when you define things and when you have some runtime code. In C or C++, or in C++, do structures exist at runtime in the absence of certain features like RTTI? Not really. They just kind of get decomposed into offset lookups on some block of memory, especially in C. You can't really see the struct after you've compiled your code. Whereas in Python, everything is executable code, or almost everything is executable code. Everything happens at runtime. And I want to talk about what happens when you define a class. Let's take a look. Consider that almost all code in Python has some runtime executable aspect to it. Class T isn't some definition that happens at parse time and then the class T is available. This is actually executable code. If I put a print statement in here, you will see this print statement is actually run. If I do something like this, it's going to blow up in some weird ways. But let's put something here. Give it an argument that it's going to ignore. You can see, it blew up because the init subclass didn't like that, but you can see that it actually runs executable code. This means that I can define classes in a for loop. I can put a for loop inside a class body. I can define a function that defines a class inside of it. I can do things like assignments. This is a very common pattern. I have a function. I want to give it 2 names. Maybe this is a really long name like application. And I want to say, app is short for application. So I can do little tricks like that. And it's very common for me to do some kind of executable code in this class body. Well, the entire class, including the class body, is executable code. Here, you can see I even have some kind of weird behavior where I can assign to a local variable, making use of a variable that's in the global scope. This is the only place where something like this actually works. And how this works is a little bit bizarre. So I don't want to go into that too deeply. Instead, I want to show you that you could use that class as an executable body to do things like automatically define methods based off of some external data. You could have a JSON file that defines the methods for this particular class and read that in, and then use exec in order to automatically create the methods that you want. And this will lead us into understanding what actually goes, what the process of defining classes actually looks like. Before we do that, though, I want to talk about protocols in general. And I want to talk about this, one of the simpler protocols we have, the call protocol. I want to talk about how this relates to metaclasses and one place where metaclasses are distinct from mechanisms like init subclass. Here's what we know. When we have a function, when we put open close parentheses after it, that's equivalent to invoking this call protocol. It's equivalent to calling this underscore underscore call underscore underscore function. And you can see this is call all the way down. We can just keep going as deep as we want. The open close parentheses basically translates into this particular protocol. Well, what you might think is when you define or when you create an instance of a class, you do the class name, open close parentheses. So that means there should be an underscore call somewhere. And what you can see is it's not this call that's defined on the class, because that call is used when you invoke open close parentheses on the instance itself. Well, where is the call that's invoked when you create the instance in the first place? There's 2 calls that are being used here, but I can only see one of them that I implement. Well, what you can think is this dispatch to these protocols, to things like len and call and whatnot, have a certain rule to them. And the rule is they must, what you do when you're trying to dispatch to one of these special underscore name protocols, with these automodel methods, is you look at the type of the object that you have, and you look for the method on that type. So if I have object open close parentheses, and it's going to call here, what it's actually looking for is it's looking for this method as implemented here. And it's going to invoke this, passing in the self parameter using mechanisms that we'll talk about in a separate session, mechanisms like the descriptor protocol. What that means is you cannot add underscore methods to an object, to an instance after the fact. Here, I've tried to add a call method just to the instance, not to the class, after the instance was created, and it doesn't work. These special underscore methods must be present on the class itself, not on the instance. Well, if you think about it, there's some layers here. An instance is an instance of a type. a type is an instance of a metatype. This is what a metaclass provides you other than the enforcement of constraints from a base type to a derived type. It provides you with the space to implement the Python vocabulary, not on object instances, but on types themselves. In other words, here, and I'll give you a very simple example to start with. Here, I have an object, and I've implemented negate on it. So I can put negate on the object. If I wanted to implement negate on the type, well, this negate is already in use for the implementation on the instance. The place I have to put this is on the metaclass. And the metaclass is uniquely the only mechanism by which you can implement the Python vocabulary on an underlying type, as opposed to on an instance of a type. So you can see here I have two negs, one that's working on the type and one that's working on the object itself. Well, this leads us very closely into how instance construction and class construction work. When you see the open-close parentheses after a type name with the purpose of creating an instance, this is actually implemented on the metaclass. And here you can see my metaclass with my metaclass call method. It is this method here which actually invokes the new and the init method on the class instance itself. And if this is a data class, it invokes like the post init as well and all of those other mechanisms. But new and init are actually triggered by this call method. You can choose not to use new or init if you want to. If you say, you know what, I'm going to add another stage to this protocol, or I'm going to collapse this protocol so there's no way to implement new or init, you can do that by just swapping out what call does. You actually have a lot of flexibility over how instances are created because you have that ultimate hook point into this vocabulary right here that says go and create an instance from this type. Now let's talk a little bit about what new and init actually do. What you can think is behind the scenes, what this looks like when you are creating an instance is you're first creating an instance of this object. So you're going to call this is going to take self.new. And here you're going to pass in wave like that. And then you're going to say self.init. And then you're going to return the object. What you can see here is that new and init are just two stages in the process of creating an instance, one before the instance is created and one after the instance is created. Init just says take an already created, already allocated instance and then initialize it, mutate it in some fashion. And new is go about actually doing things like the allocation itself in order to create this instance. Python generally doesn't give you control over where things are allocated, but because you can override new, you could actually create, say, a contiguous block of memory using a tool like NumPy or another C extension module and control how things are allocated by just intercepting at that new level. You couldn't do it at the init level because this already requires that the class instance is ready to go. It just needs to be initialized, but you could do it at the new level. Well, what this leads us to is if we have a new and an init that relate to instance creation, instance construction, where one of these runs before the instance is created, one of them runs that after the instance is created, and call that triggers these. Well, how does class construction work? Well, very similarly. On the metaclass, you have a new and an init, and one of these is triggered before the class is created, and the other one is triggered after the class is created. And so here, I do not have any code that looks like this, object equals t. I'm just creating the class, and you can see there is a new and an init, which allow you to hook into before the class was created and after the class was created, initialized. And you've seen this with the typical metaclass, enforcement of a constraint from a base type to a derived type. It usually involves hooking in before the class was created. So you can raise some, you can take a look at, say, the body of this thing, and you can raise a type error or value error, whatever you want, if the body doesn't contain some method that you expect, or you can take existing things that were defined and wrap them in some fashion, whatever you choose to do. Well, it turns out that the protocol for calling the new and the init in the process of class construction has more hook points. One important thing to know is Python is not a language where we have rigorously defined a foundational mathematics for how things work. It's more of a set of mechanical processes where people have identified we need a hook point here, a hook point here, and a hook point here. We need a safety valve here, an escape hatch here, and a way to hook into the implementation there. New and init are just two hook points related to either class construction or instance construction, depending on whether you implement it on the class or on the metaclass, that'll give you two hook points. And there's no reason why you can't have more hook points. In fact, in Python 2.6, whenever enum was created, they actually added more hook points to class construction. They added a hook point called prepare. Here's what it does. Before you do the new or the init, you run prepare. The way that classes are actually created is first, you take the body of the class and you evaluate all the code in that body. You stick all of that into a namespace. That's what this body parameter is. You pass that to new, and you pass that to init, and then you got the constructed class. Well, the namespace that you put the contents of that body into, you can actually customize. And the reason you need to do that is previously, prior to Python 3.6, when we had the split table optimization for dictionaries, where a dictionary maintained insertion ordering, well, the namespace that's used for collecting the pieces that you create in that class body wasn't ordered. So if you need to do anything fancy that required some ordering, like enum.enum needs to do, then you need to customize what kind of namespace you're working on. All prepare does is give you the ability to provide a custom namespace with custom rules associated with the namespace. It's an implicit static method. You can see here, and you can actually mark it as a static method or whatnot, and you can actually even make it a class method if you want, but I don't think there's really huge benefit to doing that. What people would do historically is they would have their prepare return something like an ordered dictionary so that the things that were created in the class body preserve the order in which they were created so that you know, oh, this attribute was created before this attribute was created before this attribute, and then you could automatically assign, for example, numbers to them, 1, 2, 3, which is what something like int enum does. There's other ways you could do this. You could use some sort of mutable, iterator of some sort, like a generator or whatnot, but the preference was to be able to kind of set some symbol and then to track that symbol in the new and to know what the original ordering was by using an ordered dictionary. Now, we don't really need prepare anymore because Python dictionaries now are guaranteed to be ordered by insertion order, which means Python namespaces are also guaranteed to match insertion order. And so the use of prepare is actually even less interesting than it was originally. But it is an example of where the protocol for creating classes has changed over time and may even continue to change if somebody needs another hook point somewhere else. One thing that you might have interacted with as well is when you use some of the boilerplate elimination tools like the collections.name tuple, you got to write the name of the type twice. T equals name tuple T. And it used to irritate people like nobody's business that they had to write T 2 places. And people tried to find all sorts of crazy ways to avoid this. Maybe name equals T, and then you pass in, name here, and then you do locals of name. Maybe we can even do this with an assignment expression. I think this right-hand side is evaluated first. Here we can try anything we can to avoid having to write the same text twice. Well, it turns out that the class construction protocol was extended to allow you to solve this kind of problem. And this is another part of the protocol, specifically set name. It turns out when you evaluate a class body and you use that in order to create the underlying class, if anything that you evaluated, anything that you put into that local scope is an object that implements the set_name method, that gets called after the body is evaluated. So you can see here I have a hook point, and that hook point knows what name I was assigned to. It knows I was assigned to the name A, name B, and name C, which means that in some cases, like when we want to do ORMs or anything else, we're doing some kind of definition. If we want to do field equals, let's do, this is maybe a database, and this is employee equals field. We don't have to write field employee like we used to in the old days, because if this thing has a set name attribute, it can see what name it was assigned to, and then use that as part of its own initialization. There are certain limitations to this. You can see the set name doesn't occur live. It occurs after the process of evaluating class body. So here you can see I defined A, B, and C. You can see that these all got triggered at the very end. And you can see that Python probably wasn't able to see the actual bind. It doesn't see A equals. It just looks through the body for anything that happens to have that set name attribute and then calls this method on it. So It's a little bit flexible here, but it's one of these examples of these ad hoc protocols that you'll see when you dig into class construction. And these are protocols which can easily change over time. We can have more of them. Probably won't remove any of these, but we can easily add more of them if we can have circumstances or if we find circumstances where this is warranted. In general, what I want you to know is Python defines protocols for every action that it performs, and everything in Python, or almost everything in Python, is executable code up to and including defining classes themselves, which means there's a protocol for how class definition works. There's methods that you implement them in a slightly different place on the metaclass. There's 3 methods that you usually interact with: the call on the metaclass, the new and the init on the metaclass, and 2 which you may interact here and there: prepare to determine how we want to create the namespace for these, and set name if we want to do some kind of trick with the things which are created and for them to know what their names were when they were defined in the class body.